Section 3.2, unit vectors, adding vectors by components. All right, so what is a unit vector? A unit vector is a vector, but it's one that has a magnitude of 1 unit, just one. I like to think of unit vectors as pure direction. So it lacks both dimension and unit. It's not giving you size or even units. It's just saying this direction or this direction. And we label it with a little hat, the little hat that will go over each of the directions. So we'll use the right-handed coordinate system, which means that the x direction is labeled by the unit vector I, or I hat. The y direction is labeled by the unit vector j, or j hat. And the z direction is labeled with the k hat. So the unit vectors point purely along those directions. And this is something that will follow your right hand. It's very useful. Now this means that we can write our vectors in terms of their components by using these unit vectors. So vector A could be written as ax times I hat. The x component is purely in the x direction, the I hat direction. Similarly, it's plus a sub y, the y component, times j hat, telling you that the y component is purely in the j direction. Great. Similarly for b, we could break vector b down into its x and y components and specify their direction with these unit vectors I hat and j hat. Now within this, the quantities of ax times I hat is the vector component. It's the vector piece of vector A. If you then have ax or ay without the unit vector, those are scalar components, or just components as before. They no longer have a direction attached, they're just a scalar, and so they're much easier to work with mathematically. So we like when we can write our vectors in terms of scalars. That's why unit vectors are really powerful. So vectors can then be added using their components, and they'll follow the simple scalar algebraic rules, right? So if we want to add vectors A and B to get vector R, we just have to focus on adding all the x components of A and B, and that will give us the x component of R. Add the y components of A and B, that will give us the y component of R, and add the z components of A and B, and that will give us the z scalar component, or component of R. To subtract, we once again will just subtract the components, right? Or we can subtract the x pieces, the y pieces, and the z pieces, and that will define our dx, dy, and dz, which give us this overall vector d. That's a combination of d in the x direction times I hat plus dy, the y component, times j hat, plus the z component times k hat, right? So this seems like a lot to take in, but this math is really simple. So this is much better than trying to do our graphical addition. It really does help. So it's worth the investment here. Vectors are independent of the coordinate system used to measure them. So we could draw vector A relative to a vertical y and a horizontal x, and we could define it relative to some theta. But we could then rotate our coordinate axes, right? And vector A would still be the same. It would be defined relative to a different angle, and the relative lengths of the two components would change, right? AY used to be much longer than AX, and with the rotated reference frame, AY is about the same length as AX. But vector A is the same. So that means that all such coordinate systems are equally valid. We don't have to keep our coordinate system up and down. And we'll use this quite a bit actually in chapters 5 and 6 when we deal with problems that are on a ramp or on an inclined plane, that we can rotate our coordinate system and it'll work just as well. All right, one more checkpoint here. I encourage you to try this one in your own time. So see if you can figure it out, and then you can check the answers in the slides. But for now, that is where we shall wrap it up.